invite a speech of Marcello Pelillo, who is a friend of our conference. He has been chair of computer vision group or computer vision track or analysis of images and video tracks for 3 years. And right now he has an opportunity to present a really nice talk. Professor Pelillo is well known in the community of pattern recognition and image analysis for his ideas in combining game theory, graph theory, pattern recognition, computer vision together, and he got really nice results. As for me, for example, I used his dominant set clustering, and it works really nice in video-based face identification and clustering on video faces. So I'm really glad that Marcello is here with us. For sure, it will be much better if the event was offline, but so everyone understands the current situation. So welcome, Marcello. You can share your screen, and we're really nice to see you in Zoom.
Thank you very much. Thanks, Andrei. First of all, let me know if you can hear me well, if you can see me. Can you hear me?
Yeah.
Okay.
Everything is nice.
Excellent. So thanks for the nice presentation, and thanks for having me here. It's really a pleasure to be here. Of course, I would have loved to see you all in person, but it's not possible. So maybe hopefully in one of the coming years. Let me share the screen. Let's see whether I can make it. Okay. Can you see my screen now?
Yeah.
Okay, good. Let me take. Okay, and then let me use. Okay, so the topic of my talk today, as Andrei was saying, is graph-theoretic methods in computer vision. I've been working on this topic for several years, and I'm happy to share with you some of our recent results in this field. In particular, Andrei already mentioned a clustering framework, which we introduced a few years ago, which we call dominant sets. And in the last few years, together with my students and collaborators, we were able to extend that notion and also to apply in this notion in several computer vision problems. So this talk is going to be a quick overview of what we've been doing on this area in the past few years. So first of all, let me talk a little bit about clustering, and we will focus on clustering on graphs, of course. In the classical clustering problem, you are given a set of objects, say n objects, and you are given a function which measures the similarity between these objects. So you can arrange these similarities into a matrix if you like. This, of course, would be an n times n matrix. But of course, you can think of this in terms of an edge-weighted graph, where the nodes of the graph represent the objects to be clustered, and the weights on the edges represent the similarity between the nodes. So the goal is to group the input objects, or if you like, in terms of graphs, the vertices of the graph, into maximally homogeneous classes. And we call these maximally homogeneous classes, clusters, of course. So here, this is one example. You have a matrix here with a number of objects. This is a visual representation of the similarity matrix, which gives rise to this particular graph. Remember, the nodes are the objects to be clustered, and these numbers, 0.1, 2, etc., these are the similarities between the nodes. So the higher, of course, the better. And given this graph, you would like to get, for example, a partition like this one. So you want to partition the objects into one cluster here, into another cluster here. One thing that the classical approaches to clustering emphasizes is that what we would like to get as output from a clustering algorithm is a partition of the input data. And this means that all the clusters are pairwise disjoint. And also, if you take, of course, the union of these clusters, you get the whole graph. Now, in many applications, this is not really what we want. In many applications, in computer vision, of course, but also in other areas, you might want, for example, to get overlapping clusters, or you might want to get only a few clusters, say 2 or 3 or less than the total number of objects. So the framework that I'm going to describe takes into account this idea, in the sense that we try to focus on the very notion of a cluster, and without focusing on the notion of partitioning the input data into disjoint clusters. So the basic question that we want to ask is not what is the best partition that I can get from my data, but more simply, what is a cluster? Is there a way to formally define a notion of a cluster, of a single cluster? This, of course, is a moral difference between the notion of a cluster, of course, and the notion of a community. There is no universally accepted formal definition of a cluster. This is, of course, an ill-posed problem, but informally, everyone would agree that a cluster should satisfy the following two criteria. An internal criterion, which basically says that all the objects inside the cluster should be highly similar to each other. But this is not enough, because we also need an external criterion, which says that all the objects outside the cluster should be highly dissimilar to the ones inside. So in order for you to provide a formal definition of the notion of a cluster, you need to take into account both criteria, the internal one and the external one. And of course, the problem is, how can we formalize these notions into a mathematically and computationally sound methods? Now, I don't have time to give you all the technical details behind this notion of a cluster that we introduced a few years ago, which is called dominant sets, but I want to give you the intuition behind that. So in the first place, let's consider a subset of vertices S and the vertex I belonging to this set. And in our framework, we introduce a quantity, which is basically a weight assigned to the vertex I relative to the set S. So we call this quantity WSI. I don't have time to give you the formal definition of this notion, but I want to give you the intuition behind this. So WSI simply measures the relative similarity between vertex I and the vertices of S minus I, so the rest of S, with respect, so it's a relative measure of similarity, with respect to the internal similarity of S minus I. Let me give you a couple of concrete examples of how this measure works. So let's consider this graph in the first place. It's a small graph with 4 vertices. These numbers, remember, these represent similarities, so the higher the better. You can see that these 3 vertices, 2, 3, and 4, they are very similar to each other. Actually, internally, the coherence of this set, consisting of 2, 3, and 4, is very high because they all share the same similarity. Now, let's ask ourselves whether it's a good idea to add this vertex 1 to the set consisting of 2, 3, and 4, in terms of the coherency, of course, of the resulting cluster. Now, the answer is probably no, it's not a good idea, because you can see that the similarity between vertex 1 and the rest, so 2, 3, and 4, is much smaller than the similarity that internally that set has. Now, this is reflected by having a weight which is less than 0. So WSI in this particular case will be negative. Now, let's consider, in some sense, the opposite situation. Again, you have a small graph with 4 vertices, 2, 3, and 4, and 1. Now, if you forget about this vertex, of course, the internal coherency of 2, 3, and 4 is pretty good, in the sense that they all share the same weight, the same similarity. And again, let's ask ourselves whether it's a good idea to add vertex 1 to this set consisting of 2, 3, and 4. Now we see that apparently this is a good idea, because the similarity between 1 and 2, 1 and 3, 1 and 4 is pretty large, 10, as compared to the internal similarity of 2, 3, and 4. So this is reflected by having a positive weight. Now, without giving the formal definition, this weight that we assign to vertices relative to a set can be interpreted as a notion of similarity relative to the rest of the set. And in particular, with its negative, the vertex is not really coherent with the rest, and when it's positive, it is. Now, this motivates our definition of a cluster, which we call the dominant set. So formally, if S is a subset of vertices in a graph G, and I is a vertex of S, we define this measure, which we call it WSI, as I mentioned before, and then we declare the set S to be a dominant set if these two conditions hold. The first one says that WSI is greater than 0 for all internal vertices, and this is basically the internal coherency criterion that I mentioned before. And the second condition is that this weight should be less than 0 for all external vertices. And this is basically the external incoherency criterion that I mentioned before. So this is one way to formalize the two criteria that I mentioned before that should hold for any cluster, the internal and the external criteria. Now, this is an example of a graph. You can see this graph here. These are the similarities between the vertices, and this is a dominant set. You can see that actually the similarity internally of 1, 2, and 3 is pretty large. You have 70, 90, and 60. And the similarities of the external loads is pretty small as compared to the internal set. Now, we introduced this framework a few years ago now in a journal paper, in the PAMI paper 2007. And later on, we discovered many intriguing connections with several branches of applied mathematics. In particular, as Andre was mentioning in his nice introduction, we established a formal connection with game theory. And in particular, we were able to show that these dominant sets are basically in one-to-one correspondence with Nash equilibria, or more precisely, evolutionary stable strategies of so-called clustering games. Evolutionary stable strategies are a notion introduced by John Maynard Smith in the 80s, and when he established the evolutionary game theory. And you should interpret evolutionary stable strategies as a stable version of the classical Nash equilibrium notion. So dominant sets can be interpreted from a game theoretic perspective. We also establish a very nice connection with optimization theory. And in particular, and this is something I'm going to talk about in the next slide, we establish a formal connection with the continuous quadratic optimization theory. And we show that dominant sets are in one-to-one correspondence with strict local maximizers of a linearly constrained quadratic optimization problem. There is a very nice and simple connection with graph theory, because we can show that dominant sets, when you have a 0-1 matrix, which means that the underlying graph is basically unweighted, the notion of a dominant set turns out to be exactly the same as the notion of a maximal clique, which is a classical notion of a community, of a cluster, if you like, in graph theoretic jargon. So we can interpret dominant sets as a generalization of the notion of a maximal clique to edge-weighted graphs. And finally, there is a very nice connection with dynamical systems theory, because we can show that dominant sets are in one-to-one correspondence with stable attractors, meaning asymptotically stable points of game dynamics, of a class of game dynamics introduced in evolutionary game theory. So, of course, I don't have time to explain all these connections now. If you are interested, of course, you might want to have a look to a recent review paper that we published a few years ago, 3 years ago, in the European Journal of Operational Research, which contains all the details. Now I want to focus on one of these connections, the connection with optimization theory. And let's focus for a moment on a situation where the affinity matrix A is symmetric. This is actually the most common situation that you might encounter. But let me also add that the dominant set framework is far more general, and it applies also to situations where the affinity matrix A is not symmetric, which means that the underlying graph is a directed graph. So the framework is very general, but now I want to focus on the spatial case when the underlying graph is is undirected, and the affinity matrix A is a symmetric matrix, which means that object I and object J have the same similarity, whether or not you exchange the role of I and J. Now, let's consider this continuous optimization problem, which is a quadratic optimization problem. Maximize X transpose AX subject to the simplex constraint. Now, this delta over here is the standard simplex, or if you like, a probability space, which is the set of all the vectors X such that all the components are non-negative and they sum up to 1. Of course, the dimensionality of this space, or if you like, the number of components of this vector, is exactly the number of vertices in the graph. So if n is the number of vertices in the graph, this is a vector of n components. Now, if you consider this function over here, and if you interpret the component of x as measures of centrality of the elements in the cluster, this function f provides us with the measure of cohesiveness of the cluster. So it makes perfect sense to try to find the vector x which maximizes this quadratic function. Now, we were able to show that the dominant sets, this was already in our original paper, dominant sets are indeed in one-to-one correspondence to strict local solutions of this quadratic optimization problem. So in other words, we can even forget the definition that I gave before, which is purely graph-theoretic, and we can focus on this continuous optimization problem. The reason why we like this continuous version of the dominant set framework is that besides the theoretical understanding and the theoretical analysis that we can do, of course, by focusing on the continuous space, we also have access to a large number of continuous optimization algorithms for finding dominant sets. By the way, if we restrict ourselves, as I said before, to the 0-1 case, which means that your affinity matrix is basically Boolean matrix, is a 0-1 matrix, where 0 means dissimilar and 1 means similar, then it turns out that, as I said before, the dominant set corresponds to the notion of a maximal clique. Now, how do we find dominant sets in practice? So thanks to the connection that we established and that I mentioned in my previous slide, we use a very simple class of dynamical systems that are quite popular in evolutionary game theory. And they have very nice theoretical properties, but they also have very nice computational properties. These are called replicator dynamics. They come in two flavors, in continuous time versions, which means ordinary differential equations, or a difference equation, so discrete time dynamics as this one. Of course, in the practical implementations of our algorithm, we do prefer the discrete time version, which is depicted here. You see that we basically start from a point in the standard simplex, and we keep iterating this map until finally the algorithm converges to some fixed point. You might notice that there are no parameters to set here. There is no step size to set. There is an implicit step size. The only thing that you need to fix in advance is the starting point of this dynamics. And this is usually the barycenter of the standard simplex, which means the uniform distribution, and also the stopping criterion. So you have to have a stopping criterion, which in our case is just stop when the difference between two consecutive points is smaller than a certain threshold. But I want to draw your attention to the fact that this dynamical system doesn't have any step sides. We don't have to fix any parameters step by step. And as I said before, this game dynamics have very nice theoretical properties. We can prove, actually, people in evolutionary game theory have proved that these dynamics will converge to dominant sets, or more precisely to evolutionary stable strategies. So the theoretical understanding of these dynamics allowed us to conclude that when this algorithm converges, it will give us a dominant set. And also from a practical point of view, it's very easy to implement in practice. This is a a straightforward MATLAB implementation in just 3 lines. You can implement this algorithm, and you have theoretical guarantees that the algorithm will find the dominant set. Let me stress to one point, though, because uh, here, contrary to what happens in other clustering algorithms, I don't know whether you are familiar with the spectral clustering or, of course, k-means. Here, we concentrate on finding a single cluster. So we extract one cluster. Then if we want to get disjoint clusters, then you throw this cluster away, and then you find another cluster, and so on and so forth. So the algorithm iteratively finds several clusters. You don't get a partition in one shot. By the way, if computational speed is a concern for your application, we do have also faster dynamics with the same theoretical guarantee, but they are much faster than this one. Now, let me point to one thing with one property of this framework, which is very interesting, especially for our computer vision applications. Now, if you run the replicator dynamics, eventually you will get a vector which has as many components as there are nodes in the graph. How do you interpret the ith component of this vector? Well, as I said before, this component can be interpreted as a measure of the participation of that vertex in the cluster. In other words, if the component is 0, this means that that component, that vertex, does not belong to the cluster. If it's greater than 0, so technically speaking, it belongs to the support of the vector, then the higher that value, the more central the point is, or the node is, within the cluster. I'm going to give you a very simple example of this behavior, because as I said before, this is a property that we typically use in many of our computer vision problems. So here you see two nicely separated clusters. These have been generated using 2 Gaussians, of course. Now, depending on the starting point, you might get this cluster or this cluster. These green points represent a dominant set, and these blue points represent another dominant set. So there are basically 2 dominant sets here. Now, let's have a look at the vector corresponding to this blue cluster, and also let's have a look at the vector corresponding to this green cluster. Here is a visual representation of these 2 vectors. You see that outside the blue cluster, which means this area over here, all the components are 0, as we expect, because these points do not belong to the blue cluster. While you can see that the value of the components of this vector become larger and larger when we get inside the cluster. So basically, you have this peak distribution, kind of Gaussian-like distribution, where the more central the point is within the cluster, the higher the corresponding value. And actually, you get a maximum here, probably at some point near the center of this cluster. And you see the same phenomenon over here. Outside the cluster, of course, you get 0, but inside the cluster, the value of the component gets larger and larger when you get inside this cluster. So this is an interesting property, because you might want to use this property in several applications. In particular, you might want to sort the elements of the vector in order to rank the elements in the cluster. In some applications, for example, you might be interested to extract a representative of the cluster. In other applications, you might simply want to get a ranking. And so this you can get almost for free by just looking into the vector X. Now, let me briefly summarize the main properties of this framework. So this dominant set approach to clustering, in the first place, although I didn't mention this explicitly before, contrary to what happens with other classical clustering algorithms, we don't need to know the number of clusters in advance, for the simple reason that we keep extracting cluster one at a time until we are done, basically. So we don't need to know the number of clusters in advance. And in many applications, this is a major difference with respect to classical approaches. Another very important feature of our framework, which distinguishes dominant sets from other classical framework, is that it's very robust against outliers. Since we are not using a purely partition-based approach to clustering, but we do extract one cluster at a time, if you are in a situation where there are lots of outliers, lots of background noise, usually dominant sets are extremely robust. And this cannot be done, of course, in a purely partition-based approach, such as spectral clustering, for example, for the simple reason that, of course, if you have outlier points, these will get assigned to some clusters. While in this case, you simply stop the algorithm when you find that you are done, and then all the other elements can be thrown away. I already mentioned the property that we can rank the clusters element according to centrality. Although I didn't explain how to do that, and I'm not going to use this property, we have ways to extract overlapping clusters as well. And it naturally generalizes, very naturally actually, to hypergraph clustering problems, where instead of having pairwise similarity relationship, you have higher order similarity relationship. So formally speaking, you don't have anymore a graph, but you have a hypergraph. So in a paper which we published a few years ago in PAMI, we show how to generalize this framework to hypergraph clustering as well. And also, I already mentioned this property. We make no assumption on the structure of the similarity matrix. The similarity matrix could be symmetric, non-symmetric, could contain negative values, positive values, it doesn't matter. This is a major difference with respect, for example, again, to spectral clustering. And because in spectral clustering, since you are relying on the eigenvalues of the Laplacians, and you know that you get real eigenvalues when you have a symmetric matrix. So the symmetric assumption is of fundamental importance in spectral clustering. And if in your application you have a non-symmetric matrix, for example, you might want to compare probability distributions, and you want to use Kullback-Leibler divergence to measure the distance between distributions. And we all know that the Kullback-Leibler divergence is non-symmetric, although there are, of course, symmetric versions of that. But there might be situations where the similarity function is not symmetric. And in that case, the only thing that you can do if you use spectral clustering, for example, is to symmetrize the matrix. And in this way, you are losing some information, of course. While in our framework, we can still use the dominant set framework and without any need to change the underlying matrix. So over the past few years, dominant sets have been applied in a variety of computer vision applications, but also outside computer vision. Andre was mentioning one application in his lab, and dominant sets have been applied in problems ranging from image and video segmentation to anomaly detection or video summarization, image matching, 3D reconstruction, human action recognition, and so on and so forth. But I was also glad to see that the framework is being applied quite successfully in a variety of other domains, such as neuroscience, bioinformatics, medical image analysis, and so on and so forth. Now, I want to focus in the second part of my talk, I want to focus on some applications of dominant sets, and also, as I said before, to some recent developments in the theory, which allowed us to apply the framework on novel computer vision problems. But in the first place, let me mention this nice application. This is a paper we published a few years ago in collaboration with the Italian Institute of Technology. The problem here is to detect conversational groups, meaning groups of people talking to each other in images and sequences. There's a technical name for these conversational groups. Sociologists call them F formations. There's a definition given in a classical textbook by Cholek and Kendon. An F formation is defined in this way: whenever two or more individuals in close proximity orient their bodies in such a way that each of them has an easy, direct, and equal access to every other participant's transactional segment. So, of course, in order to talk to another person, you have to be close to that person, and also you have to orient your body in a certain way. Otherwise, it's quite difficult to talk if I'm just oriented in a totally different direction. So this, as I said before, sociologists call this notion F formation. And here you can see some examples of conversational groups, or if you like, F formations. And these are taken from a data set which is publicly available that we used for testing our algorithm. And these are some typical situations when you can entertain a conversation with other people. Now, this is a problem which finds application, especially in the video surveillance, but also in other areas such as social signal processing or social behavior analysis. Now, we set up a very simple architecture, which contains as the core of the system, there is the notion of a dominant set. So this is the pipeline. So the first thing that the system does, of course, is to detect people in an image or in a frame, if you are talking about a video. And and there are, of course, off-the-shelf algorithms that we are using to do that. And once we extract a person from the image, we are interested in particular in the position, so the x, y coordinates of the person, and also we are interested in the orientation of the head, because this is of fundamental importance to understand whether two or more people are talking to each other. And so these are information that we extract using, as I said before, off-the-shelf algorithms. Now, we use a notion which is very important in this context, which is called the frustrum of visual attention. Formally speaking, the frustrum represents the area in which a person can sustain a conversation, and is defined formally by an aperture and by a length. There are little cones, in other words, attached to you. You can see some of these cones here. This is the frustrum of this person. This is a frustrum of this person, etc. And we use this notion to set up an affinity matrix. So in our framework, once we detect the persons in a frame or in an image, we build a graph where the nodes represent the persons detected in image, and the weights on the edges is a measure which tells us the amount of overlap of these frustra. The more overlapped are the frustra, like in this case, for example, you see three people, probably they are talking to each other, and the three frustra, they have a lot of overlap. We provide a probabilistic characterization of the frustra. I don't have time to explain all the technical details, but at the end of the day, we were able to measure the amount of overlap between pairs of frustra. So you can see these three frustra intersect a lot, while this one does not, and presumably this person is not part of this conversational group. So we build, at the end of the day, we build a matrix, an n by n matrix, or a graph, and then with n vertices. And then the problem was to find or to extract the dominant sets from this graph. Now, you can well imagine that in this framework, we don't know in advance the number of conversational groups that you have in a frame or in an image. And so we cannot really use classical approaches such as spectral clustering or similar approaches, because there we need to know the number of clusters in advance. And in this kind of application, of course, we don't have access to this information. So we keep extracting conversational group using the algorithm that I mentioned before. Now, these are some results, a very quick overview of the results. The rows of these two tables represent competing algorithms. Ours is represented by these two rows, and this third one, these are three variations of the basic idea using basically different similarity functions. And these are competing approaches. Here you can see different benchmark data sets that are publicly available. One refers to a coffee break at a conference. Another one refers to images in a poster session, again in the conference. These are images taken at a cocktail party. These are synthetic images. And this one, I don't remember exactly what it is, but this is another benchmark data set. So here you can see the precision, the recall, and the harmonic mean, the F1 measure. Of course, the higher, the better. And you can see that almost always, I would say always, the algorithm is able to beat the state of the art and to get much better results than other existing approaches. By the way, we wanted also to compare our framework with spectral clustering, this green row that you can see here, by feeding the algorithm with the right number of clusters, which is of course not one would do in practice, but the results were pretty poor, as you can see from the experiment. So we are pretty happy about this idea of applying dominant sets to this problem. And nowadays, although a few years have passed since we published this paper, nowadays dominant set clustering is still one of the method of choice for this kind of problems. Here you can see some concrete examples on a few images. Here, yellow means the ground truth as taken from the training set. Green means our method, and red means another approach, which was one of the competing methods. And you can see how the algorithm is able to perform pretty well in these examples. Okay, now let me mention another more recent development of the theory and also applications of dominant set. In a recent paper, which we published last year in PAMI, and dominant sets for constrained image segmentation, we introduced a variation of the notion of a dominant set, which we called constrained dominant set. And we applied this idea to several problems. In this paper, we applied this idea to interactive image segmentation and also to co-segmentation. But we also use this framework in other problems, such as person identification or tracking, multi-camera tracking, or geolocalization. Let me first introduce this notion of a constrained dominant set, and then we're going to see how we use this idea for the interactive image segmentation. So suppose you have a graph and you want to find the cluster of this graph, but besides the graph, you also have a vertex, and you want to find a dominant set which contains that vertex. So this is the reason why we call this problem constrained dominant set, because here you don't just want to find an arbitrary dominant set, you want to find a dominant set which contains a given vertex, or, and that's more general, instead of giving you a single vertex, I can give you a subset of vertices, this S here, and you want to find a dominant set which contains at least one of these vertices. So formally speaking, you are given a graph, and you are given a set of vertices S. You have a parameter alpha, and now we define this parameterized family of quadratic programs. Maximize X transpose times this matrix over here times X, subject to the usual simplex constraint. Now, what is this matrix that you can see here? So very simply, besides the technicality, this is basically the matrix A, where on the main diagonal of the matrix, you put minus alpha in correspondence to the elements outside S. So it's basically the same matrix as before, but before the matrix A contained just 0 elements, and here you have minus alpha only in those positions corresponding to the element outside S. So formally speaking, you build a matrix like this one, where I hat S is this matrix over here. Of course, when alpha is equal to 0, then you get back to the original problem that I mentioned before. You simply maximize X transpose AX over the standard simplex. Now, what happens if you have an alpha which is positive now? Now, there is a property which we proved in our paper, which says that if we set alpha large enough, and in particular larger than the largest eigenvalue of the corresponding submatrix, remember here, we are assuming that the matrix A is symmetric. So in this particular application, we make the assumption that the matrix A is symmetric. And so we know that all the eigenvalues of A and all the eigenvalues of all submatrices are real. So by setting alpha greater than the largest eigenvalue of the submatrix corresponding to V minus S, we will this problem will have a support containing elements of S, which means that there will be at least one element, probably more, which belongs to the cluster that you extract. Now, we use this idea in the first place to attack the famous interactive image segmentation problem, which is a classical problem in computer vision. Here we are given an image like this one, and there's a user who provides you some information concerning the objects he or she is interested in. For example, the user might draw a bounding box around the object of interest, maybe a tight bounding box like this one, or a loose bounding box like this one. Or another option would be that the user just draws a scribble over a part of the object he's interested in, or maybe, like in this case, he might want to use two kinds of scribble, one for the object, the blue one, and the red one is for the background. So our algorithm takes as input the image and the constraint expressed by the scribble or by the bounding box, and provides you the segmentation of the prominent object that the user has pointed to. Now, one of the nice features of this framework is that now usually in computer vision, there are two kinds of algorithms for interactive image segmentation. One uses bounding boxes as the way in which the user interacts, and the other ones use scribbles. While in our framework, we were able to attack the two problems within exactly the same framework. And the idea is quite simple. Let's consider, for example, the scribble case. So of course, the image is represented in terms of a graph where the nodes are the pixels and the edges contain a weights which is proportional to the similarity between the pixels. Now, if the user draws a scribble, like in this case, basically he's is pointing to some vertices in the graph. So remember the set S that I mentioned before. And so basically we are asking for a dominant set which contains at least some elements of this scribble. So this is basically the constrained dominant set problem, and we use it to attack this version of the problem. In the case where you have bounding boxes, like this case, for example, if you have a bounding box like this or like this, basically you use the information on the bounding box for extracting the background. And so by this simple trick, we can attack both the scribble-based and the bounding box-based approach. Now, of course, we tried our algorithm over several benchmark data sets. Here are some examples. These are the results. And this is with the scribble-based approach. These are state-of-the-art algorithms, and that's the error rate. And we were able to beat all the state-of-the-art algorithms by a significant extent. And that's what happens with bounding box methods. Here we measure the Jacquard index, which is a measure of the overlap between two areas. Of course, here the larger, the better. And again, we were able to substantially advance the state of the art. So we have 93, 93, or 95 against the best one was 84. And here are some examples of the results we got on these benchmark data sets. These are bounding boxes. This is ground truth, by the way. And this is bounding box based. And this is scribble based. And the algorithm is able to find the correct object very reliably. And these are other examples with bounding boxes and scribble. Now, let me mention another very recent paper. We published this paper last year again, where we used the notion of constrained dominant set for completely different problem. Another classical, actually two problems to tell the truth, very much they're classical problems in computer vision. One is tracking, or in particular, multi-target tracking with multiple non-overlapping cameras. And a variation of this problem, or a version of this problem, is person re-identification, which is related to tracking. Let me start with person re-identification, which is probably simpler to understand, at least how we approach the problem. So in person re-identification, which is a classical problem with applications in, for example, video surveillance, You have two or more cameras. Maybe they are far away. The field of view do not overlap. Like in this situation here, you have camera A and you have camera B. Suppose that there are some people walking over here. At some point, one of these persons gets captured from camera A, and then of course, since he or she is walking, it will disappear. But after a while, it will reappear again over here. So the problem here is to recognize an individual over different non-overlapping cameras. So you want to know that the person which appears here at this very moment is the same person which appears here maybe a couple of minutes ago. So formally speaking, the problem can be cast in this way. You're given a gallery of persons, of person images taken from one camera, say from camera A, and you have a new image, which is called the probe, and you want to basically match the probe against the gallery. This is an example of how difficult the problem is. This is a person, suppose this person here is captured by camera B, and these are all the persons captured by camera A. And you will see the problem is to find this person here, despite variations, of course, in maybe in motion and in appearance. And it turns out that this is the person. So it's a very challenging problem with, as I said before, applications in several areas, including, of course, video surveillance. Now, most recent approaches, instead of using a single frame, they use short tracklets, so a small, very short tracks of maybe 5 or 10 consecutive frames. And this allows you to consider not only appearance information, but also motion information. So here is the situation. You get a probe here, and you get a gallery here. This is taken from another camera. And the problem is to check whether this person here is present here. So we build a graph. Let me just jump this. Okay, we build a graph. This is the graph, where the nodes of the graph represent all the elements in the gallery, and we also add the probe. And then we find the constrained dominant set, which contains the probe. And the similarities on the edges are the standard similarities that are used in this framework. They contain feature extracted by a convolutional neural network, and also we use motion information. Now, going back to the previous slides, what's the difference between the traditional approaches and ours? Now, usually in the standard methods, typically people try to build a better feature representation for objects, or better distance metrics between the probe and the gallery. And then they finally rank the images from the gallery based on the pairwise distances from the query. Our approach is different in principle because we use very standard features and very standard distance metrics. We extract, as I said before, a constrained dominant set for each query, where the constraint is the probe. And so the question is, extract the dominant set which contains the probe. And then we perform a ranking over the short-listed clips. And this allows us to take into account not only the relationship between the probe and the gallery elements, but also the relationship among the gallery elements. And this is a feature that other algorithms do not have. And that's the final rank. So basically, we build a graph. This is the seed. So I want to find a dominant set which contains the seed. Here we go. We get the dominant set. We rank the elements, and this is the final rank. So we tried this idea over the largest video-based rate identification data set available, which was built a few years ago. These are images taken from 6 near synchronized cameras with more than 1,000 identities and more than 3,000 distractors. The tracklets were 25 to 30 frames long. And these are our results. Of course, each row corresponds to other state-of-the-art algorithms. And this measure is a measure of the quality of the results. And the higher, the better in particular. And of course, ours was able to get the best results. So at the time of publication, that was the state-of-the-art method. Nowadays, probably there are other methods which have been introduced, but ours is still one of the method of choice for this problem. And these are some examples. You see, these are some probes, and these are some gallery elements. The green elements correspond to exact matchings. The red ones correspond to bad matchings, but the first one is always the right one, at least in these examples. Now, let me quickly talk about a related problem. Conceptually is different, but there are, of course, similarities between personal identification and multi-target, multi-camera tracking. So here, as before, we are in a multi-camera setting, possibly non-overlapping cameras, like in this situation, and you want to track people or objects from one camera to the other. So we developed a pipeline which contains the notion of a dominant set in 3 different levels. So let me briefly mention how the system works. Suppose you have n cameras, like in this case, camera 1, camera 2, camera n. So in the first place, since we are interested in detecting humans, we used off-the-shelf algorithms for human detection. So you end up with a bounding box around each person detected in a single camera. And then we built short tracklets by simply measuring the amount of overlap of the bounding box in consecutive frames. Now, these short tracklets become the nodes of a graph where we look for dominant sets. And that becomes the first layer of our framework. We do this independently for all the n cameras. So the result of the first layer is to provide tracklets. So the nodes are short tracklets, and the final result is a set of tracklets. Then we build another graph, again, independently from each camera. And the goal now is to put together all these tracklets in order to build tracks, which are much longer, of course. And this is done again, camera by camera, independently. Finally, the third layer tries to combine the results taken from the independent cameras. And we built a third layer where now the nodes of the graph are the tracks found in the previous steps. And then we extract again a dominant set, which will give us the final result. So let me show with a simple example how this works. So remember, we first extract short tracklets by measuring the amount of overlap between consecutive bounding boxes in consecutive frames. Then we build a graph where here the nodes are the short tracklets. The edge weights try to combine both appearance and motion. And in particular, as far as appearance is concerned, we use standard CNN features, while motion, we just measure the constant velocity. So now we have a graph, and we extract dominant sets. So this is one dominant set, and which gives rise to one tracklet. This is another dominant set. Remember that we extract them in sequence, and this is another tracklet. And we keep going this way until eventually we find a number of tracklets. Okay, so this is the result of the first layer. And then we have the second layer where now the nodes are the tracklets found in the previous layer. So we do exactly the same thing as we did before. And the result now is a number of tracks. So you can see here what happens with the algorithm. This is basically one track, and this is another track, and this is another track. I don't know. Oh, here we go. Now, these operations are performed in parallel on the several cameras, on the different cameras. Let me see whether I can start a video. Maybe it's not working. Let's see. Here we go. This is a video which shows how the system works. Here we are in the very preliminary phase of human detection. We are using off-the-shelf algorithms for doing this. And then this is the tracks that have been extracted in the single camera with our framework. And you see how the algorithm is pretty robust in extracting all the tracks with all these people. This is done, as I said before, camera by camera. Okay, let me go ahead. Now, remember, the final step tries to combine all the tracks found in the different cameras. That's the place where all the information of the different cameras go together. So we build another graph where the nodes now represent the tracks found in the cameras, in the individual cameras, and the edge weights are, of course, the similarity between the nodes. And then we extract tracks across cameras, like in this case, or in this case. You see that here, for example, which is what sometimes happens, these two tracks in the original camera were kept separated for some reason, while we were able to put them together in the cross-camera association task. So these are the results we got on the standard benchmark data set. I don't know how much time I have, but I'm running out of time. By the way, our results were better than competitors. And here are some concrete examples on some images. Like here, this is taken from camera 1. And you can see, for example, this person, 212, is the same person here. This is within camera. And you see across another camera, the same person is assigned the same number, and so on and so forth. So these results are pretty good on this standard benchmark data set. Okay, I don't think I have time to talk about this other application, but give me 1 minute to just mention the problem. This is another paper that we published last year in PAMI. We use dominant sets for geolocalization. So the problem is, suppose you take a picture of a street or a building in your city, or you come to Venice, for example, you take a picture of some bridge, and then you have a data set of images with the corresponding GPS coordinates, and you want the system to tell you approximately the GPS coordinates where you are. So we built a pipeline where dominant sets play a major role, and we were able to find, to obtain an algorithm which is 200 times faster than previous approaches, and we got an accuracy which is 20% better than the previous state-of-the-art approaches. I don't have time to give you the details. If you are interested, you might want to have a look at the paper. So let me just jump to the conclusions now. So in conclusion, the dominant set framework and related concept have shown to be a very powerful tool for attacking a variety of different computer vision problems. We've seen interactive image segmentation, geolocalization that I just mentioned, group detection, personal identification, tracking. And of course, we are trying now to combine this framework with deep learning to get, especially Siamese networks, to get more accurate similarity measures. And this is a paper which we just published last year at ICCV 2019. These are some references that you might want to have a look at if you are interested. That's the original dominant set paper. This is the hypergraph extension to it. This is the constrained image segmentation paper, the geolocalization paper, the conversational group, the tracking paper. And if you're interested in a review of this work, you can have a look at this paper, which was published in the European Journal of Operational Research. So I'm done. Thanks for your attention. And of course, I'm happy to take questions. Thank you very much.
Yeah, thank you, Marcello, for very nice talk. So we have not much time, but probably someone has question.
Yeah, sure.
I have one question. What do you think of deep clustering approaches, and particularly some deep clustering applied to the graph data, where basically the algorithm is of clustering is integrated into loss or objective functions? Is this perspective direction of work, in your opinion?
Yeah, thanks for this question. That's an interesting question, because as I mentioned in my last, actually, this is well, we are trying now to combine deep learning with clustering. As you might have noticed, there is no deep learning in all the framework that I've just explained. There is no notion of deep learning. But I think the next step, and actually we're working on this, is to combine deep neural networks, and especially the idea, I just mentioned this in the conclusions, the idea of extracting and learning the similarities from data. That's much more powerful approach than just using similarities from scratch. I'd be very curious to to establish a formal correspondence between dominant set clustering and more recent graph-based deep learning approaches. But at the moment, we don't have any formal property about that. What we are doing right now is just to integrate these two things, and the integration comes in the computation of the similarities. So basically, we'll learn the similarity. And this paper here that I just mentioned before provides us with a way to to learn the similarities in an end-to-end manner and to integrate these similarities in person identification. So this, I think, is going to be an exciting line of research trying to integrate dominant set clustering with deep learning, and we just started working on this.
Thank you very much.
You're welcome.
Thank you. Other questions? Okay, so I have a very small question. So you presented some method for co-segmentation or some manual. So when you need some manual binding box, for example, around an object, and then you provide the good segmentation part for this. So my question is, have you tried something like object detectors when you detect this object, not manually, but you use some
that's a great question.
Not good detector, yeah, and how your algorithm will work in it.
Thanks for the question. Actually, what we did was to, interactive segmentation, when was originally introduced in computer vision, assumed that you have a user, and the user just, draws a bounding box or maybe draws a scribble, and that's the reason why it's called interactive image segmentation. Nowadays, we have standard benchmark data sets for doing this, and we tried that on those benchmark data sets. But of course, that bounding box can come from an object detector. And although we didn't directly work on this, in principle, it can be done. So you can imagine a situation where you have an object detector which throws a bounding box like the one we were been using for tracking, for example, a bounding box around the objects of interest, and then you run the constrained dominant set. We haven't done that because we just use a standard benchmark data set, and we were working on interactive image segmentation. But of course, it can be done. And I'm eager to know if you are willing to apply this idea. I will be very happy to know what happens.
Okay, so thank you. Other questions? Okay, it seems that we are done. So let me thank Professor Pelillo for this
talk.
It was
a pleasure. Thanks.
Providing a talk for ICE conference, and thank you very much.